At last, the last section of Unit 4. Graphs of logarithmic functions. Yay, logarithms. So if you guys can remember back to when we did exponentials, and you can remember the rules of an exponential graph, that will help you understand the rules of a logarithmic graph. Why? Because exponentials and logarithms are inverse operations. That means exponential functions and logarithmic functions are inverse functions. So if you can remember again, remember back to your inverse functions rules, the domain of the inverse is the range of the original. The range of the inverse is the domain of the original. So the domain and range literally switch places. Not only do the domain and range switch places, but their asymptotes switch places as well. All horizontal asymptotes of the exponential become vertical asymptotes of their logarithmic inverse. Bless you. And that is why logarithms have a restricted domain, whereas exponentials have a restricted range. So the domain of exponentials, all real numbers. The range of exponentials, greater than 0. Remember, because they have a horizontal asymptote at the x-axis? So those values for domain and range switch places for the logarithm. The logarithm's domain is positive numbers only being plugged into it as its argument, and its range then is all real numbers. Remember when I was telling you that the argument of a logarithm must be a positive number? That is why. The argument must be a positive number because it's the inverse of an exponential. You can't raise a positive number to any power and ever get a negative value. Therefore, you can never take the logarithm of a negative value. It's just not possible. Not only that, you could also never get the value of 0 with exponentials, so you can't plug a 0 into logarithms. Because the parent exponential has the x-axis as a horizontal asymptote, y equals 0, the parent logarithm has the y-axis, x equals 0, as its vertical asymptote. They switch places. If your exponential base was between 0 and 1, you would have this dotted exponential decay graph. If the exponential base was between 0 and 1, that's old material. Well, if you switch all the x's and the y's, what you get is a reflection over the line y equals x, and you get what I would call an upside down logarithm graph. That's what that looks like. The textbook authors show you 2 points. They show you a comma 1 and 1 over a comma negative 1. Let's not worry about that too much. I have my own easy way to graph logarithms. You might have developed your own ways or been taught your different ways in Algebra 2 Honors, so I'm not going to worry too much about what that is saying. I'll set us up for success in a moment. Now, the one on the right, that is showing exponential base if it was y equals a to the x, an exponential base greater than 1. So this would be exponential growth here. And if you switch the x's and the y's, net result is reflecting over the line y equals x. You get what, to me, represents the standard logarithm graph. It is asymptotic to the y-axis and goes up and to the right forever increasing. Again, I'm not going to worry too much about those 2 dots they have there. I have my own methods. Yes, Zach?
Just trying to make sure I remember something correctly.
Mm-hmm.
So let's say hypothetically, you'd have a logarithmic equation that'd be y equals log parentheses x plus 1 and parentheses.
Okay.
That would
log of x plus 1.
It would like clip off at it would go like all the way down infinitely.
It does point down to infinity, yes. But what would happen is what you just described, if you do a plus 1 inside the parentheses in the argument, you've shifted the entire graph to the left one, which includes the vertical asymptote. Now the vertical asymptote has scooted off of the y-axis from x equals 0 to x equals negative 1.
Wait, but I thought things couldn't be 0 or less.
The argument can't be 0 or negative. But the numbers you plug in can be, as long as they don't break the rules of the argument.
So, wait, so if there weren't any parentheses, would that mean it flips off?
No.
Wait,
If there's no parentheses, then what you've done is you've shifted the graph up or down.
then what's the thing you have to do to make it click off?
You can't. Nothing. That's a square root graphs have a beginning, but all logarithms, as long as you don't restrict their domains, all logarithms will point down to negative infinity in one direction and go up to positive infinity in the other direction.
Oh.
So you kind of already hit on my shortcuts that what I like to consider shortcuts for graphing. You really only need 3 things to graph a logarithm. Those 3 things are the vertical asymptote and 2 points. Why 2 points? Because then you know its shape. That's it. That's the only reason why. It's just like when we were graphing exponentials, I only ever found 2 points. It's the same idea. So for exponentials, I found the horizontal asymptote, and then I found 2 points. For logarithms, I found the vertical asymptote, and then I found 2 points. Part A says find the domain and range. Well, the range is easy. The range of all logarithms is the same. It's all real numbers. I'm going to write it right here. Domain. Range. Range is simple. Negative infinity to positive infinity. I'm not going to use the set notation that they used because you don't need to, so I would rather use this. The domain is restricted, though. Remember, the argument must be greater than 0. So if you're trying to find the domain of a logarithm, what you do is you take the argument and you set it greater than 0, and then you solve for x. What that tells us is that this one's domain is all numbers bigger than positive 1. Not including positive 1. Strictly bigger than. So for part B, when it tells you to find any asymptotes, you already did. It's what makes the argument equal 0. That's your vertical asymptote. So the 3 things that you need to know, and then I'll finish answering the question. The 3 objects that you need, it works like this. What makes argument equals 0? That's your asymptote. So you'll find that number. So what makes our argument equal 0? X equals 1. There you go. X equals 1. The next thing that you want to do is, what makes, you don't have to write these words every time, obviously, but this is your thought process. What makes the argument equal 1? And the reason why I want the argument to equal 1 is, regardless of what the base of the logarithm is, the moment the argument equals 1, the logarithm has the same value every single time, 0. And then last, so that's how you find one of your 2 coordinates. So it'll be x equals whatever number makes the argument equal 1, and y equals whatever you get when the log has a value of 0. Okay? Meaning, did you get to add 1 or 2 or something afterwards? But we're going to evaluate. So for us, what makes our argument equal 1? 2. So that happens at x equals 2. And if you plug 2 in, you get a log that has a value of 0 and then plus 1. Because log base 2 of 1 is automatically 0. So what that says, if the argument equals 1, f of x would be 0 plus 1, which is just 1. So we have a point at 2, 1. And the last extremely easy thing to do with logarithms is what makes the argument equal the base. The reason why is because when the argument and the base match, the log has a value of 1. So what x would we need to plug in for our argument to be the same as our base? Our base is 2, so what x do I need to plug in? 3. So if I plug in 3, what I'm getting here is a value of 1 plus, 1. Because log base 2 of 2 is 1. Those are the 3 things you need to sketch this graph. Now, IB wants us to do more than that. Part C says to sketch the graph. And it says find F inverse and explain how to verify your answer. Okay, so here's what I'm going to do. I'm going to sketch the graph real quick with the knowledge I have. Bless you, I think. I already found the asymptote, and then I'll find the axes intercepts. Okay, we'll go that route in just a second. But let's sketch this guy. Vertical asymptote at x equals 1. And then the next x values go to the right, so I don't need a left side of this graph, really. So x equals 1, vertical asymptote. Then I have a coordinates at 2, 1, and coordinates at 3, 2. Will they always go by 1s like this? No, it just happened to this time, because there was no vertical or horizontal stretching or shrinking involved. So the graph looks like this. So yeah, it's asymptotic to the number x equals 1. So what is the y-intercept? There isn't one. There is no y-intercept. Do some logs have y-intercepts? Sure they do. If you shifted it left, it'd have a y-intercept. We find y-intercepts the same way for everything. You plug in x equals 0. You're not allowed to plug in x equals 0 to this one, though, because we have a restricted domain. We're only allowed to plug in numbers that are strictly bigger than 1. We do, however, have an x-intercept. And the directions told us to find the axes intercepts. So they want us to find the coordinates of that point. You don't know at what x that occurs, but you do know what y equals there. What does y equal? 0. So if you would like to find that x-intercept, you set y equal to 0 and solve for x. 0 equals log base 2 of x plus, minus 1. Come on, come on. Oh my gosh. There we go. And then there's a plus 1 out here. And now we just solve for x. Good thing we know how to solve for x, right? Subtract 1 from both sides. Log base 2 of x minus 1 equals negative 1. I need the log base 2 to disappear. Exponential base 2. Yay! Like that. Deuces. What you get is x minus 1 equals, well, 2 to the negative 1. That's just 1/2. That's 0.5. So you add 1 to both sides? Oh, okay. Yeah, this thing is crossing the x-axis at 1.5. So that point has coordinates 1.5, 0. I'll be real with you, I was actually expecting an ugly answer, but it's not. It's a pretty answer. Part C, I have forgotten. What was it? Oh, sketch the graph. Okay, we did that. Part D says find the inverse. Well, we just walked our way through the process of finding the inverse. You switch x and y, and then you solve for y. So part D, yeah, part D, I guess. Let's do it over here. I have space over here. Let's switch x and y. X equals log base 2 of y minus 1 plus 1. And now we just have to get y by itself. So you subtract 1 from both sides. Log base 2 of y minus 1 equals x minus 1. Cancel the log base 2 with an exponential base 2. Oh, fun. Y minus 1 equals 2 to the x minus 1. And then you just add 1 to both sides. So our inverse, and actually I'm not going to write y, I'm going to write f inverse. Where's my undo arrow? Let's write f inverse instead of y equals. F inverse of x equals 2 to the x minus 1 plus 1. And if you're really, really crazy, if you wanted to, and you don't have to, but if you wanted to, you could say that this is 1/2 times 2 to the x plus 1. Because that negative 1 power is a 1/2. If you wanted to, you could. And the only reason why you would do that is just to reveal all the transformations. You don't have to. Honestly, this is plenty good. That's plenty good. I just figured I would do it. It said to explain how you would show that this is the inverse, right? Is that what it said? Explain how to verify your answer. Do you guys remember how to verify that two things are inverses of one another? That's what it is. In order to prove that they are inverses, you have to compose them in both order. So I would just say, show that f of f inverse of x equals x, and you have to do both. F inverse of f of x equals x. If both of those things are true, then you have found true inverses of one another. So log graphing, really not that bad. Finding the domain is essentially finding the vertical asymptote, and then you just find two coordinates. What makes the argument equal 1? What makes the argument equal base? That's it. If the argument is 1, your log has a value of 0. If the argument equals base, your log has a value of 1. Keeping life simple. And that last part that showed that stuff, that's just to prove that they're inverses. We good to move? Nobody's still writing? Okay. What's next? And by next, I think this is last. Is this it? Or is there more? Cool. I'm going to bring this chapter to a close. Consider the function, that's written all weird. Let's just write it like this. F of x equals e to the x minus 3. There's no need to be extra. Okay. It says find the equation that defines f inverse. That literally means find the inverse. So A. Switch x and y. X equals e to the y minus 3. And now we just get y by itself. How am I going to cancel that base e? Natural log, because it's log base e. Natural log both sides. So we take the ln of both sides. I'm actually going to write it. Ln of both sides like this. These cancel. Y minus 3 equals the ln of x. And then just add 3 to both sides. F inverse of x equals the ln of x plus 3. Now, that plus 3 is not in parentheses, so that plus 3 is not part of the argument, okay? It's a vertical shift. 3 units, up 3 units is what that's telling you to do. Sketch the graphs of f and f inverse on the same set of axes. Okay, well, e to the x has, well, not always pretty values, right? So what do these things look like? How about I sketch them first and then figure out the domain and range of yada, yada, yada. The horizontal asymptote of any exponentials that has not been shifted up or down is automatically the x-axis. So our original curve looks something like this. There's f of x. Our f inverse looks like, let's do orange and blue, like this. what's going on here is they are, oh, I forgot to write F inverse. Notice how non-specific I was with the stuff? There you go. This is line y equals x. There, I've graphed them on the same sets of axes. Okay. It says state domain and range of each. Well, for f, how do I want to say the domain of f? It's the blue one. Okay, I'll just do it in blue. Okay, domain of f. Yikes. F of x. Its domain. It's an exponential. It goes forever left and right. All real numbers. But its range. It has a horizontal asymptote that it does not cross. Gets really close to it though, right? The x-axis, y equals 0, and then goes up. So from 0 to infinity. So the domain and range of f inverse are the exact same values, just switched. Domain for that logarithm from 0 to infinity. Range for that logarithm, all real numbers. And I cannot see the last question. Find any asymptotes and any intercepts. Okay. Well, for f of x, we have a horizontal asymptote at y equals 0. So for f inverse, you have a vertical asymptote at x equals 0. Let's work with f of x. It doesn't have an x-intercept. It only has a y-intercept. How do we find y-intercepts of any graphs? You plug in x equals 0. Well, it says f of x is e to the x minus 3, right? So let's see what f of 0 is. That's e to the negative 3. That's 1 over e to the third. So you have a y-intercept at 0, 1 over e cubed. So guess what the x-intercept of f inverse is? Is right. X-intercept would be at 1 over e cubed, 0. Don't do the algebra again. That's it.